Living in a consumer civilization that has turned millions of square kilometers of ocean into massive, dead zones, the disappointment of a teenager during a diving trip sparked the largest ocean cleanup campaign in human history, removing more than 110 million pounds of plastic from river systems and oceans across the planet. After being collected, millions of pounds of plastic are transported into massive processing lines where they are sorted, cleaned, shredded, and regenerated into raw materials for an entirely new industry. So how can these gigantic floating garbage zones be intercepted, collected, and processed on an industrial scale? Join Agriculture Insight as we explore the story behind this extraordinary achievement. Amid the massive ocean currents of the North Pacific exists a region containing trillions of pieces of plastic swirling endlessly for decades, covering an area of approximately 1.6 million kilometer squares, or roughly 3 times the size of France. And the world does not have just one, but as many as 5 gigantic ocean garbage patches like this. These are not solid floating islands of trash as many people imagine, but rather a plastic soup dispersed across an enormous area where ocean currents continuously gather plastic from all over the world. But the real danger does not lie in the massive pieces of plastic visible to the naked eye. It lies in the process by which they are continuously broken down by sunlight, ocean waves, and friction over many years until they become nearly invisible microplastics. These particles then enter the marine food chain and eventually return to the human body itself. In ecological logic, every year of delay in cleanup means all future intervention efforts become more complicated and expensive. But humanity delayed that process for more than 7 decades, ever since petroleum-based plastics began exploding on a global scale in the mid-20th century. Scientists estimate that this region accounts for only about 1% of the world's ocean water, yet contains up to 7% of all floating surface microplastics globally, equivalent to around 1.8 trillion pieces of plastic with a total mass reaching 100,000 tons. For many decades, experts almost unanimously agreed that cleaning this area was impossible. Estimated costs reached tens of billions of dollars, and using traditional methods such as ships and nets, the process could take thousands of years. But right in the middle of what seemed like a hopeless situation, a bold idea began to emerge. Instead of chasing plastic across millions of square kilometers of ocean, humanity would let the ocean currents themselves concentrate the waste in order to capture and transport it into massive industrial processing systems before it permanently degrades into microplastics. It was an approach that went against conventional intuition, yet perfectly aligned with the way the ocean itself operates. And to turn that seemingly irrational idea into reality, a 16-year-old Dutch boy named Boyan Slat emerged with an approach completely different from every ocean cleaning method that had existed before. 1 year after a disappointing diving trip off the coast of Greece, where he saw more floating plastic bags than fish, in the fall of 2012, at the age of 18, Boyan Slat stepped onto the TEDx Delft stage with an 11-minute talk titled, "How the Oceans Can Clean Themselves."
However, I believe the Great Pacific Garbage Patch can completely clean itself.
For months, Slat's seemingly naive question received almost no attention and gathered only around 2,000 views. But by February 2013, when technology and environmental media outlets began discovering it, everything changed almost overnight. Donations quickly started pouring in, forcing Slat to make the biggest decision of his life: continue pursuing his aerospace engineering degree or drop out of university to chase the ambition of cleaning the oceans. At the time, his bank account contained only around $300 in savings. Slat chose the ocean. Just days after the video went viral, the project received approximately $90,000 in donations. and by September 15, 2014, the total had reached $254,282, becoming the most successful non-profit crowdfunding campaign in history at that time. And from that moment on, in order to prove that the oceans could truly clean themselves, the ocean cleanup was officially born, with its first mission keeping millions of pounds of plastic stationary in the middle of the ocean. The ocean cleanup first had to solve an extremely complex physics problem: how to create a structure light enough to continuously float on the ocean surface, yet durable enough to withstand large waves, ultraviolet radiation, salt water, and mechanical stress for years in the open sea. The system's greatest distinction lay in its gigantic mechanical structure, designed as a U-shaped floating barrier approximately 600 meters long. To create this structure, the ocean cleanup used around 50 sections of high-density polyethylene pipe, each nearly 1.2 meters in diameter, a material commonly used in offshore oil and gas systems because of its corrosion resistance, impact durability, and ability to maintain stable buoyancy in harsh marine environments. Most importantly, the assembly joints were built using steel connectors, reinforced cables, and flexible linkages that allowed the entire structure to bend with the motion of the waves rather than resist them. Beneath the floating pipes, engineers installed a 3-meter-deep skirt made of technical fabric. This depth was carefully calculated to retain most plastic floating near the surface, while still allowing marine life to swim underneath, reducing the risk of harming the ecosystem. The operating principle of System 001 was based on a very small difference in movement speed between the system and the plastic waste. While floating plastic is pushed faster by wind and waves, Wilson generates greater hydrodynamic drag, causing it to move slightly slower and gradually funnel debris into the curved central section like a gigantic floating trap in the middle of the ocean. In September 2018, System 001, nicknamed Wilson, was officially towed out of San Francisco Bay to begin its first real-world test in the largest garbage patch on Earth. However, the system quickly revealed serious limitations. Unstable ocean currents and inconsistent drifting speeds prevented the system from keeping plastic concentrated inside the barrier, causing much of the debris to escape back into the ocean instead of remaining trapped for collection. By the end of 2018, an 18-meter section fractured due to material fatigue at welded connection points, forcing the system to be towed back to Hawaii after collecting only around 4,000 pounds of plastic in 4 months. The figure was far below initial expectations. As a result, System 001B was introduced in 2019, an upgraded version designed specifically to solve the problems that had caused Wilson to fail. Beneath the system, a parachute-style floating anchor approximately 6 meters long creates additional hydrodynamic drag, allowing the entire structure to move about 0.3 to 0.5 meters per second, slower than the floating plastic on the surface. This very small speed difference is enough for tens of thousands of plastic fragments to continuously accumulate in the central area, while retaining thousands of pounds of waste during each collection cycle. After around 6 to 8 weeks of operation at sea, the plastic accumulated in the center of the system is lifted onto the support vessel using industrial cranes. On the ship's deck, workers begin preliminary sorting of fishing nets, hard plastics, large containers, and organic contaminants before all the plastic is packed into containers and transported to recycling facilities. This process is extremely difficult because much of the plastic has drifted through the ocean for years, exposed to saltwater, UV radiation, and marine organisms that degrade and contaminate the material, making sorting and recycling far more complex than conventional land-based plastic waste. Its composition is also astonishing. Fishing nets account for 46% of the total mass, while between 75% and 86% of the plastic originates from offshore fishing activities. After more than 10 upgraded versions since System 001 Wilson, by 2025, the ocean cleanup had removed more than 25,000 tons of plastic waste from river systems and oceans worldwide, equivalent to the mass of tens of thousands of gigantic Labubu figures being pulled back out of the sea. But the ocean cleanup quickly realized that cleaning the oceans alone was not enough, because around 1,000 rivers, representing less than 1% of the world's river systems, are responsible for nearly 80% of the plastic continuously flowing into the oceans every year. Among them, Thailand, China, Indonesia, the Philippines, and Vietnam alone release as much ocean plastic as the rest of the world combined. This discovery changed the nature of the problem itself. Instead of focusing solely on cleaning up plastic that had already drifted into the ocean and dispersed across millions of square kilometers, the organization shifted toward a strategy of intercepting plastic at highly concentrated entry points, where river flow and geometry allow for far more efficient intervention in terms of energy and cost. From this logic, the interceptor system was developed as an automated river plastic collection platform. Each system is approximately 24 meters long, nearly 16 meters wide, and permanently anchored along riverbanks using heavy-duty piles and tension cable systems. Extending from the interceptor's main body, a floating barrier stretching dozens of meters is positioned diagonally along the direction of the current to continuously guide floating waste toward the central intake opening. As debris approaches the system, an automated conveyor belt approximately 1.5 meters wide begins operating, continuously lifting plastic from the water surface into the vessel. The entire system operates on solar energy, using around 32 solar panels installed on the roof to power the conveyor belts, sensors, and AI systems that monitor waste flow in real time. One of the most notable projects in the United States is Interceptor 007, deployed on the Los Angeles River, one of the most plastic-polluted urban rivers in America, where more than 220,000 pounds of waste were intercepted within the first months of operation before reaching the Pacific Ocean. But pulling millions of pounds of plastic back out of rivers and oceans was only the beginning. The next challenge was how to transform that chaotic mass of waste into reusable industrial raw materials on a massive scale. As soon as the material is brought back to land, the entire volume begins undergoing a careful sorting process based on polymer type, aging level, and recyclability. In reality, around 80% of the collected plastic has deteriorated and become contaminated to the point where it is no longer suitable for commercial recycling. This portion is typically processed through energy recovery systems or strictly controlled destruction methods to permanently remove it from the environment, instead of allowing it to continue breaking down into microplastics in the ocean. Only around 20% of the plastic remains stable enough to proceed into material regeneration lines. This mainly includes hard plastics, HDPE, polypropylene, and especially nylon fishing nets with lower levels of degradation. After being separated, the plastic continues through large high-pressure washing tanks to remove salt, sand, oil, and attached marine organisms before being fed into high-speed industrial shredders. Here, the material is cut into fragments several centimeters in size before continuing through polymer separation systems using optical sensors and float sink density sorting. The plastic that meets final quality standards is then melted at temperatures of approximately 180 to 280 degrees Celsius inside industrial extruders before being stretched into strands and cut into small recycled plastic pellets. Because of the extremely high costs of collection, transportation, and processing, ocean recycled plastic is often sold at prices up to 5 times higher than conventional recycled plastic, ranging from around $2,000 to more than $5,000 per ton, depending on material quality and purity. These plastic pellets are then sold back to manufacturers to produce sunglasses, packaging, electronic components, furniture, and many commercial products labeled as ocean recycled plastic. Some recycled ocean plastic has now even begun appearing in globally distributed commercial products. Coldplay once partnered to use plastic collected from rivers and oceans to produce recycled vinyl editions for one of their album releases, while Kia also partnered with the Ocean Cleanup to integrate recycled ocean plastic into next-generation automotive interior components. From a teenager standing in front of floating plastic bags in the Mediterranean, humanity has now, for the first time in history, begun truly addressing ocean pollution on a massive scale, proving that what was once considered impossible is sometimes simply a problem that has not yet been approached with the right way of thinking. By mid-2026, the Ocean Cleanup had removed more than 110 million pounds of plastic waste from rivers and oceans, operating 21 interceptor systems across 10 countries, with a team of around 200 employees from all over the world. The estimated cost of completely cleaning the Great Pacific Garbage Patch is $7.5 billion over 10 years, and the mission remains unchanged, removing 90% of floating ocean plastic by 2040. Even so, the amount of ocean plastic currently collected and recycled still accounts for less than 1% of the global plastic recycling industry, while the world continues producing more than 400 million tons of new plastic every year. And as plastic continues flowing into the oceans every single day, this battle has perhaps only just begun. In your opinion, what is more dangerous? The millions of tons of plastic already floating in the oceans, or humanity continuing to produce more of it every day? Plastic is not the only material that modern civilization is learning how to regenerate, because every year hundreds of billions of glass bottles are also entering one of the most complex industrial recycling systems in the world. Few people realize that glass, an everyday familiar material, is placing growing pressure on global natural resources. Creating it from scratch comes at a high cost. Billions of tons of sand are dredged every year, causing severe erosion and damage to river ecosystems. Beyond the massive energy consumption and CO2 emissions, impurities in raw sand are also a #1 enemy, aggressively corroding the refractory bricks of million-dollar furnaces. That is why glass recycling has become a key solution for preserving this precious resource. Environmental leaders such as Switzerland and Germany have now reached recycling rates of up to 90%, 3 times higher than that of the United States. Why do you think this enormous gap exists? Many people wonder whether recycled glass is truly clean enough for food use, but the truth is that it is just as pure as new glass. Unlike plastics or rubber, which can easily undergo structural changes, glass is completely inert. It does not absorb odors, does not retain color, and most importantly, does not release any microplastic particles into the human body. That is why, at the strictest frontiers, such as vaccines and high-grade pharmaceuticals, the world still has no perfect substitute for glass, a gold standard for human safety. And now join us as we explore this remarkable rebirth, a journey that may seem vast in scale yet begins in the simplest of places, the household waste bins of millions of families. For this circular process to begin, the first requirement is a stable supply of used bottles and jars. In modern recycling systems, collection largely relies on fleets of specialized trucks, machines designed exclusively for glass. On average, a major operator such as Biffa in the United Kingdom must cover around 3,000 households per day to ensure not a single fragment of recyclable glass is left behind. This pressure becomes even more intense during the summer months, when warmer weather drives up demand for cold beverages. The resulting surge in discarded bottles and jars forces collection trucks to operate at full capacity, making multiple collection rounds per day instead of the usual single run. But door-to-door collection is not the whole picture. In most EU countries, networks of reverse vending machines are now installed throughout supermarkets, activating source-level sorting right at the point of disposal. Consumers simply place an empty bottle into the machine. The system scans it, sorts it, and returns a small cash refund, typically around 10 to 25 cents, depending on the country. A soda bottle you've just finished drinking, instead of becoming waste, can instantly turn into loose change for your next purchase. This approach not only encourages people to participate voluntarily in collection, but more importantly, it supplies recycling plants with a stream of pre-sorted, cleaner, and far more uniform glass than ordinary mixed waste. From here, the journey of transporting tens of tons of bottles and jars to specialized processing plants begins. Large trucks, each capable of carrying between 20,000 and 30,000 bottles per trip, operate continuously, moving between supermarkets and collection points to consolidate the material for recycling. The processing cycle is formally initiated when heavy-duty industrial loaders move in on stockpiles of waste glass rising several meters high. Each bucket can hold multiple tons of material, which is transported in a controlled manner across the yard to maintain a steady feed rate into the plant. At the intake point, the glass is discharged directly into receiving hoppers. Driven by gravity, the mixture of fragments slides down reinforced steel chutes where conveyor systems come into operation. From this moment on, the glass stream, still mixed with sand, dust, and contaminants, is carried deep into the processing line, where successive stages of cleaning and sorting will ultimately determine the quality of the entire downstream recycling process. After being broken down, the waste stream makes its first stop at a multi-stage vibrating screening system. Here, high-frequency vibrations separate natural contaminants, such as dust, gravel, and sand, from the main glass flow. This stage serves as a surface cleaning step, allowing the material to be more clearly exposed and prepared for more advanced sorting processes. However, mechanical equipment at this stage cannot fully remove larger or lighter contaminants, such as paper labels, plastic films, or pieces of wood. As a result, a manual inspection zone follows immediately after the vibrating screens. Specialized workers are positioned along the conveyor belt to visually monitor the stream and manually remove any remaining foreign objects. The combination of mechanical separation and human judgment ensures that the material meets cleanliness standards before entering the more sophisticated downstream separation systems. But even after screening and sorting, troublesome obstacles always remain hidden within the pile of broken glass. Bottle caps. These are the enemies of the furnace, as they do not melt like glass and instead introduce contaminants capable of ruining an entire batch. At this stage, massive electromagnets suspended above the conveyor belt come into operation. Generating extremely strong magnetic fields, they lift and extract every steel bottle cap or screw upward, completely separating them from the glass stream moving below. Thanks to this decisive step, the cleanliness of the material is raised to around 80%. Clearing the way for the critical crushing stage that follows. Once most contaminants have been removed, the glass enters a critical stage of structural transformation. Crushing. Large fragments are fed into hammer mills where high-speed rotating hammers deliver repeated impacts, breaking the glass down into uniformly sized particles. To maintain quality control, any pieces exceeding the specified size are captured by screening systems and redirected back into the crushing chamber. The result is glass cullet with a fineness comparable to manufactured sand. Reducing glass to this granular form not only allows it to melt more quickly in the furnace, but also helps save up to 40% of the energy required compared with using entirely virgin raw materials. Immediately after crushing, the material stream is passed through a high-capacity extraction system. Here, powerful air currents strip away and blow off any remaining microscopic label fragments still clinging to the surface. This final cleanup step ensures the glass reaches maximum purity before entering the laser-based sorting stage. The final, and also the most sophisticated stage in the cleaning process, is optical sorting. At this point, glass fragments are spread thin and allowed to fall like a waterfall in front of a system of high-power laser sensors. In a split second, these sensors scan each fragment to accurately analyze its color and material composition. As soon as a differently colored piece of glass is detected, or more dangerously, a stray piece of ceramic, the system immediately activates compressed air nozzles. These air jets fire with millimeter-level precision, blowing the contaminants out of the main stream in just milliseconds. Absolute precision at this stage is vital, because even a tiny amount of color deviation or ceramic contamination can completely ruin the transparency and quality of the entire batch. After passing the laser system's inspection, the clean glass fragments move along the conveyor belt to the final collection area. Here they are separated and stored individually according to 3 color codes: clear, green, and brown. A step that may seem simple, but in fact directly determines the value and efficiency of recycling. Few people know that clear glass accounts for the largest proportion and has the highest economic value. However, with just 1% colored glass mixed in, a melting batch will immediately become cloudy and unable to regain its original transparency. Therefore, color separation is mandatory to control purity, enabling factories to recycle directly into new products of the same type without incurring the cost of removing color impurities. After being refined, recycled glass cullet cannot be fed directly into production, but must first go through a raw material blending stage. The basic composition starts with pure silica sand to ensure transparency. Next comes soda ash to lower the melting temperature, and limestone to increase the mechanical strength of the finished product. Depending on specific requirements, manufacturers add minerals such as alumina, dolomite, or metal oxides to adjust color and physico-chemical properties. In this batch mixture, recycled glass accounts for 20 to 70% of the total weight. This proportion allows the mixture to melt faster, directly saving about 40% of operating energy and reducing carbon emissions compared with using only virgin raw materials. Once the components reach the standard proportions according to the preset formula, the mixture is thoroughly blended and moved to the melting stage. The batch is fed into a high-capacity gas-fired furnace system. Here, the temperature is maintained at around 1,250 degrees Celsius to carry out the material transformation process. Because the heat radiated into the surrounding environment is extremely intense, the operating crew must wear specialized heat-insulating protective clothing and thick gloves to control the melting pot safely. After about 24 hours of continuous firing, the raw material mixture melts completely and turns into a highly viscous liquid. During the next 5 hours, the molten glass is kept at a stable temperature for the refining stage. This is a mandatory step that allows air bubbles to escape, ensuring the purity and uniform structure of the glass stream. To transform the molten glass stream into products with specific shapes, the mold system is an indispensable component. Based on designs created in specialized CAD software, molds are manufactured from cast iron or special alloy steel. These materials possess extremely high heat resistance, up to 1,400 degrees, ensuring they do not deform when in continuous contact with molten glass. After fabrication is completed, the mold sets are installed on the production line, ready for the forming stage carried out directly inside them. When the mold system is ready, the process enters the double blow stage. the standard method for producing hollow containers such as soft drink bottles or pharmaceutical jars. The process begins by cutting the molten glass stream into gobs of uniform weight. These gobs enter the preliminary mold at around 1000 degrees Celsius, the ideal temperature at which glass reaches stable viscosity, allowing smooth forming. Inside the preliminary mold, a first blast of compressed air is blown forcefully from above, pressing the molten glass tightly against the mold walls. The result of this step is the formation of a parison, a hollow structure in which the bottleneck is clearly shaped, while the body remains soft and retains a large amount of heat. Immediately afterward, the glass parison is transferred to the final mold set, located right next on the production line. Here, a second blast of compressed air is injected directly into the center of the parison, stretching the softened glass outward until it fully conforms to the fine details inside the mold cavity. Although this process appears very fast from the outside, in reality, the entire system of valves and sensors must be synchronized with precision down to 1/1000 of a second. It is precisely this extreme level of technical control that enables corporations such as Coca-Cola or Heineken to ship hundreds of thousands of bottles every day with absolute uniformity, ensuring that every single bottle meets the same standards before global distribution. Although today glass packaging accounts for only about 15% of Coca-Cola's total output, it is by no means outdated. On the contrary, for many discerning consumers, glass remains an irreplaceable choice. It keeps drinks cold longer, does not retain odors, and does not alter flavor. As a result, the fizz and sweetness are preserved intact, a purity that plastic or aluminum has yet to fully replicate. First, we move straight into the beating heart of the circular economy, where household waste is no longer buried in landfills but reborn as biological fertilizer. From anonymous trash bags, an industry worth over $60 billion a year is emerging, turning environmental burden into sustainable revenue and new life for the planet. To turn waste into money, the first step is not technology, but separation. Fruit peels, leftover food, paper, and leaves are sorted out to be composted or recycled. In contrast, metals, plastics, and non-biodegradable materials are collected separately to prevent contamination, clearing the way for the real value hidden in waste. After preliminary sorting, tens of tons of household waste are transported each day to processing plants, where they officially enter the most critical stage of their regeneration journey. Here, waste is no longer a chaotic mix of debris, but a raw input for a tightly controlled industrial process. First, the sorted waste is conveyed onto industrial belts and fed directly into high-capacity shredding systems. Inside the crushing chamber, alloy steel blades rotate at high speed, powerful enough to break down bones, hard shells, and even the toughest organic materials. This process reduces the waste into uniformly sized particles, increasing surface area and creating ideal conditions for microbial activity in later stages. More importantly, shredding reduces waste volume by up to 40%, saving storage space and significantly lowering transportation costs. A modern industrial shredder can process between 10 and 20 tons of waste per hour, equivalent to the combined output of 1,000 manual laborers. Once shredded and homogenized, the organic waste mixture is sent directly to the composting area, where it is formed into long windrows or transferred into enclosed composting tunnels. Here, the life-critical process of organic fertilizer truly begins. Native microorganisms are rapidly activated, penetrating every particle and breaking down organic matter in a controlled biological process. Driven by intense microbial activity, the temperature of the compost mass gradually rises and stabilizes between 55 and 65 degrees Celsius. This temperature range is high enough to eliminate most pathogens, harmful bacteria, and completely destroy any remaining weed seeds. At the same time, Turning and moisture spraying systems are operated regularly to maintain optimal oxygen levels and humidity. Through this process, what was once a chaotic pile of waste transforms into a closed biological system, cleaner, safer, and ready to move into the maturation stage of high-quality organic compost. After the active decomposition phase, the compost is transferred to a curing and biological stabilization stage, where its final quality is shaped. Beneficial microorganisms continue working quietly, completing the transformation of organic matter into stable humus. After the curing stage, the compost is screened to define its final value. The humus stream passes through rotary screening systems, separating material that meets the size standard of under 15 millimeters, accounting for up to 80% of the total mass, while coarser fractions are recirculated for further processing. As a result, the organic fertilizer achieves high uniformity, stable moisture levels below 25%, and is free of contaminants, or ready for packaging. From raw waste at the start, the final product becomes a standardized agricultural input that can be applied directly to the fields. After leaving the screening line, compost is not yet released to the market. It must first pass through the final checkpoint, the QC lab. Here, samples are carefully analyzed for biological stability, including moisture, pH, and potential risks from heavy metals or residual pathogens. Only when all indicators meet regulatory standards, with moisture maintained around 50 to 60%, is the compost approved for use. This final control step eliminates risks at the last stage, ensuring a safe and consistent product. Once certified, the compost moves directly to the packaging line, where each bag completes its regeneration journey, ready to return to the fields as new agricultural value. Organic waste treatment reduces the amount of waste sent to landfills by 40 to 60%, easing pressure on the environment and urban systems. The resulting compost not only supplies nutrients, but also improves soil structure, enhances water retention, reduces nutrient runoff, and lowers dependence on chemical fertilizers. When properly regenerated, household waste is no longer a burden, but a circular resource that nourishes sustainable agriculture. More than 1/3 of the world's freshwater supply is used for irrigation, while clean water sources are becoming increasingly scarce and pollution continues to spread. Faced with this paradox, humanity has found a new path, transforming dirty water into irrigation water, regenerating the flow of life from what was once considered hopeless. To turn thousands of tons of foul-smelling wastewater generated every day into water safe enough for irrigation and the environment, the initial treatment process serves as a critical line of defense. As wastewater silently flows through underground pipes into treatment plants, it carries not only contaminated water, but also diapers, wet wipes, plastics, and fabrics. This is why public restrooms are forced to post warnings not to dispose of paper or waste into toilets. Each year, careless flushing habits generate hundreds of tons of non-biodegradable debris, enough to cripple wastewater treatment systems worth millions of dollars. Water that passes this first control stage then flows into grit chambers, where the flow is deliberately slowed, allowing heavy materials such as soil, sand, and stones to settle at the bottom. After coarse waste is removed, the wastewater enters a critical screening stage in the grit chamber. Flow velocity is tightly controlled and combined with precisely regulated aeration to trigger natural separation. Heavy particles such as soil, sand, and gravel quickly settle to the bottom, while the lighter water continues downstream. Each week, the system can collect and treat nearly 1 ton of inorganic grit, preventing damage to equipment in subsequent stages. From here, the wastewater flows into the primary settling tank, where gravity becomes the primary filter. After approximately 5 to 6 hours, Most of the heavy sludge settles at the bottom, while clarified water separates above. Automated scrapers continuously remove settled sludge and floating scum, transferring them to digestion tanks. Through this step alone, more than 50% of suspended solids are removed, creating a stable foundation for the biological treatment and reuse stages that follow. From the settling tank, the wastewater enters the aeration basin, the living heart of the entire treatment system. Here, every cubic meter of water contains hundreds of millions of microorganisms working continuously in an oxygen-rich environment, created by constantly rotating aerators that keep the water in motion. These microbes convert waste into energy for the cleaning process. Within just a few hours, toxic ammonia and most organic compounds are broken down directly in the flowing water. No longer a matter of passive filtering or settling, the aeration basin functions as a precisely controlled artificial ecosystem, where more than half of the plant's overall treatment efficiency is determined before the water moves on to its final stage. Depending on discharge standards, the water continues through multiple cycles of biological treatment, including aeration and settling. After 18 to 24 hours, the flow enters a chlorine contact tank to eliminate pathogens, before leaving the plant and returning to the environment. Treating wastewater into clean water for agriculture reduces pressure on increasingly scarce freshwater resources, while transforming urban waste into a reusable resource. Treated water not only ensures reliable irrigation, but also helps maintain soil moisture under harsh climate conditions. When quality is strictly controlled, reused water limits environmental pollution, reduces discharges into rivers and lakes, and supports sustainable, circular agricultural production. Once burned or buried in oblivion, sugarcane bagasse and coconut husks are now rising as the black gold of the green era. More than 500 million tons of agricultural residues each year are being regenerated into biochar, a strategic carbon material for soils and the climate. From piles of ash, a billion-dollar market is emerging, offering a bold solution to soil degradation and the global carbon crisis. The biochar production process begins by fully harnessing two of the most abundant agricultural residues, sugarcane bagasse and coconut husks. At sugar mills, immediately after the juice is fully extracted, sugarcane bagasse is collected and stacked into mounds as high as hills. Under sun and wind, moisture gradually evaporates, leaving behind a resilient cellulose framework, the backbone of biogenic carbon. Once optimal moisture levels are reached, the bagasse is fed into fine grinding systems. Steel gears rotate continuously, cutting, tearing, and breaking down coarse fibers into a smooth, uniform material stream. Each grinder processes around 500 kilograms of dry bagasse per hour, ensuring a steady feed for the pyrolysis stage. A particle size below 5 millimeters not only allows for even heat transfer inside oxygen-free reactors, but also determines the porous structure, the very soul of biochar. At that moment, sugarcane bagasse officially sheds its identity as waste, becoming a strategic input for the carbon materials of the future. At the same time, another equally important supplementary feedstock, coconut husks, is collected from food processing facilities. In the past, more than 70% of coconut husks were discarded as waste, piled into massive heaps that consumed land and caused pollution. Today, that burden has been transformed into a resource. After being sun-dried to reduce moisture content below 20%, the husks are fed into vertical shaft grinding systems, where high-speed steel blades continuously cut, tear, and loosen their coarse structure. Within minutes, the tough outer shells are converted into a light, fibrous mixture, an ideal material for the pyrolysis process. After fine grinding, the mixture of sugarcane bagasse and coconut fiber is fed into a screw press, where a slowly rotating steel shaft generates immense compression, compacting the biomass and forcing it through a forming die. This process produces high-density biomass briquettes or pellets with a uniform structure. By being tightly compressed, the material achieves more efficient heat transfer inside the pyrolysis reactor, while gas flow remains stable and controlled. As a result, the biochar forms with fewer fractures and a more consistent overall quality. There was a time when every Israeli child grew up memorizing one rule: turn off the tap while soaping. A habit that became almost a survival instinct in a land where natural fresh water accounts for less than 1% of the territory. Israel is not the hottest place in the Middle East, but it is among the harshest: hot, arid, and chronically short of water year-round. Trapped between the massive furnaces of the Sahara Desert and the Arabian Peninsula, the country endures brutal climatic disparity. While the north still receives seasonal rainfall, precipitation drops sharply toward the south, falling below 25 millimeters per year, equivalent to just a 30-minute rain shower in a temperate climate. Moreover, scarcity exists not only in the skies but also beneath their feet. Israel has almost no inland rivers large enough to sustain agriculture. Its only lifelines lie deep within coastal, highland, and Negev desert aquifers, finite treasures that risk saltwater intrusion if overexploited. For this reason, Israel could not survive without creating its own solutions. Beginning in the 20th century, instead of praying for rain, the nation chose to turn scarcity into a strategic advantage, actively producing water through technologies unlike anything the world had seen before. To supplement its water supply, Israel chose an exceptionally smart approach: desalinating Mediterranean seawater. With a long coastline, stable salinity, and minimal exposure to natural disasters, these waters allow mega-scale plants to operate 24/7, regardless of weather conditions. The key lies in reverse osmosis technology. Seawater is forced through ultrafine, semi-permeable membranes under extremely high pressure, allowing pure water molecules to pass through, while salts and impurities are retained, producing water that meets domestic consumption standards. What truly sets this technology apart, however, is not filtration alone, but energy recovery systems. By harnessing residual pressure from the concentrated brine stream to compress incoming seawater, Israel has reduced electricity consumption by up to 40%. As a result, production costs have fallen to a record low, less than $1 per cubic meter, among the lowest in the world. The outcome is striking. Around 80% of Israel's domestic water supply now comes from the sea, virtually eliminating dependence on natural rainfall. However, desalinated water is extremely expensive to produce and transport, so it is prioritized primarily for domestic use. To sustain large-scale agriculture in the desert without draining the national budget, Israel activated an often overlooked resource: urban wastewater. This solution has propelled Israel to the global lead, with up to 90% of its wastewater reused, 3 times the rate of the United States. At megascale treatment plants, wastewater containing organic pollutants and microorganisms is fed into massive aeration tanks. Here, bacteria act as natural decomposers, consuming and breaking down harmful organic compounds, transforming dark, contaminated flows into basic clean water. Next, pressure filtration systems and centrifuges completely remove solid impurities and sludge from the stream. This closed-loop process ensures that not even the smallest debris escapes, preparing the water for the most critical purification stage beneath the ground. The water is then directed to desert reservoirs for soil aquifer treatment, the most crucial step in the water regeneration chain. It slowly percolates through sand layers, reaching depths of up to 100 meters, using the earth itself as a vast biological filter to fully eliminate bacteria and remaining contaminants. From this point, the regenerated water reaches a purity comparable to drinking water, sustaining over 60% of agricultural land in the Negev desert at a cost only one-third that of desalinated water.